All right, so today we're going to dive a little deeper into actually writing some proofs. So we're going to prove some statements about segments and angles. We're going to talk a little bit about special angle relationships and some of the theorems involved with those guys too. Okay, so first things first, what is a proof? A proof is a logical argument that shows a statement is true. Okay, and this can be done a lot of different ways. We're going to talk about a two-column proof. Two-column proof is called that because it has two columns. There's a column for statements and a column for reasons. We're going to want to remember that all of our reasons, again, need to come from definitions, theorems, postulates, properties, or corollaries, which are kind of like theorems. But statements and reasons that show a logical, show an argument in logical order. There are other types of proofs. Two-column proof is nice because it's structured, it's sequential, but there is a particular way in which you have to do it. Okay? And then a theorem, of course, is a statement that can be proven. Not only can it be, but it needs to be proven. So let's just dive into writing a proof. Okay? So, we've got that diagram and that given information. And we need to come up with a series of statements and reasons that helps us go from knowing that the measure of angle 1 equals the measure of angle 3 to proving that angle EBA and angle DBC are equal. All right, now in a proof, you always start with the given. We have to start somewhere. And the only thing that we know that we can write in our proof right now is the given. All of your statements and all of your reasons are going to come from, just a little bit better, either the diagram or from something said prior in your proof. And so we need to put something in our proof so that we can write something from it. And the most logical place to start, again, is the given information. So angle 1 is equal to angle 3. That was given to us. There's no other reason for knowing that. Now, it's been marked in the picture also. But that was because it was given to us. The information was told to us. So we had no geometric reason to know that. It just was given to us. So we start there. The second statement is always the hardest one to write. What do I write next? And quite literally, it is looking at the diagram or looking at the given information and writing something because you know that, because you see the diagram, because you have the given information. Write something that comes from one of those two places. And you're going to freeze up here because, one, you're not really sure what to write, and number two, you don't know if it's really going to help. And really, I don't care if I know right now if it's going to help or not. If it's true, if it has a good geometric reason, in other words, the definition, theorem, postulate, corollary, those kind of things, then I'm going to write it. And I'll figure out later if it helps me or not. So the first thing I'd look at, not a whole lot I can do from the given. But if you look over in the diagram, you'll see that angle DBC, the measure of angle DBC is equal to the measure of angle 1 plus the measure of angle 2. If you add those two angles together, they'll equal that bigger one, angle DBC. So I can write the measure of angle DBC is equal to the measure of angle 1 plus the measure of angle 2. And I know that because of the angle addition postulate. Okay? All right, I don't know if it's going to help much, but I know that's true. And it must help a little bit because I'm talking about angle DBC now, and that's what I want to prove. That's one of the angles I want to prove equal. So I guess I'm on the right track. Now, if I can do it for that angle, for that bigger angle, then there's another angle addition that I can use, and that's going to be the one with angle EBA. So the measure of angle EBA is equal to the measure of angle 2 plus the measure of angle 3. And that's from the angle addition postulate. Okay. All right. So again, not real sure if that's going to help, but whatever. I know that that's true. So now I look. Not too much else I can do as far as angle addition goes. But we do know this. If 1 is equal to 3, if angle 1 is equal to angle 3, then I can use substitution. Now I can plug in an angle 1 anywhere I see an angle 3 if I wanted to. Well, how about right here? If I do that, then I'll have the measure of angle EBA is equal to the measure of angle 2 plus the measure of angle 1. And that was just by substitution. Okay. Well, if you look again, I've got 1 plus 2 here, and I've got a 1 plus 2 here. That means that I can substitute angle DBC in for this 1 plus 2 right there. So now I can go, the measure of angle EBA is equal to the measure of angle DBC, and that's by substitution again. And if you look, that's exactly what we wanted to prove. And so we're done. That's it. Okay. Next one says, you try. I'm guessing we may not be quite that ready for it. So let's build this proof that you just saw from the ground up again, and then I'll give you an opportunity to try the next one as we're trying to get used to just writing these statements and reasons and that kind of thing. Okay? So we have that diagram. We're given that AC is equal to AB plus AB. And then we want to prove that AB is equal to BC. So again, we need some statements and some reasons. Okay. Again, you got to start somewhere, and we might as well start with the given information. So AC is equal to AB plus AB. And that's given. Okay. Now what? Well, we used angle addition in the last proof. Maybe we can use segment addition here. That's what you got to do. Every time you do a proof, pull in some of the strategies from that proof for your future proofs. We simply did angle addition before. Why not do segment addition here? AB plus BC is going to be equal to AB. We know that's true by segment addition postulate. Right? Okay. Well, oh wait, sorry, I miswrote that. AB plus BC is equal to AC. Well, we also used substitution last time, and if you look, we actually have that going on again. AC is equal to AB plus AB. So I can take this and substitute it in for AC down here. So that we get AB plus BC is equal to AB plus AB. And that's just by substitution. Okay, so those are the strategies we used before, and that's gotten us pretty far, but we're not quite finished. So what now? Well, we see a couple of ABs here. What if we subtracted AB from both sides? That's allowed because of the subtraction postulate. Now, you don't necessarily have to show this actually subtracting the ABs out. In a geometric proof, in an algebraic proof you would, but I'm going to show it just so you can see where it's coming from. But if I subtract those out, all I'm doing is subtracting the same piece from both sides, and that's allowed by the subtraction postulate, the subtraction property. And if you notice, it's exactly what we wanted to prove here and here. And so we're done. So there's really no better way to do this than to just kind of have you dive in. Okay? So here's a proof here. In your notes, you have to prove two parts, part A and part B. But once you get to part A, it's one more step to get to part B. So we can make that jump pretty easily. So just worry about proving part A. Go ahead and get started. Write in the given. Then write the next statement and see if you can't see where to go from there. You can pop on the video a second and see how you did as far as writing your first proof. All right, so here's what you needed to come up with, and it's a lot of what we've seen already. One little thing that we haven't, or maybe two, but the given, M is the midpoint of AB. From there, what do we know because M is the midpoint? Well, because M is the midpoint, that means that the two segments, AM and MB, must be equal. That's the definition of midpoint. Right? Then we can use what we did before, which is the segment addition postulate. AM plus MB has to equal AB. Then we recognize right here that we can substitute. We can substitute that AM in for that MB. And when we do that, we get this step 4. So AM plus AM equals AB by substitution. And then we can combine those like terms or simplify. AM plus AM is 2AM. And that's what we wanted to prove. We wanted to prove that AB was equal to 2AM. Now, part B. Part B has you proving that AM is equal to 1/2 AB. That's just one more step. That's dividing by 2 by the division property. And then you have AM equals 1/2 AB. So there you go. Your little introduction into proof writing there, and your homework's going to have you do a little bit more of this. So we can develop a thought process here. Okay? All right, let's move on to the last section here. There's a couple of angle pair relationships that we need to develop some theorems from, some proofs of some theorems for, so that we can use these theorems down the road. Now, the first theorem is pretty obvious. The first theorem is called the right angle congruence theorem, which simply states that all right angles are congruent. That's fairly obvious, but it's a theorem that needed to be proven at some point, and so we do that here as well. So if we're given just any two right angles anywhere, angle 1 and angle 2 are right angles, right? We want to prove that 1 and 2 are congruent. So how do we go about doing that? Right? Well, here's our proof. We always start with the given. The given is that angle 1 and angle 2 are right angles. That's given. What do we know about angle 1 and angle 2 if they're right angles? Well, hopefully you're saying that the measure of angle 1 is equal to 90 and the measure of angle 2 is equal to 90. Now they're using the same reason, which is the definition of right angles. That's what tells us that if an angle is a right angle, that its measure is 90 degrees. So since they're using the same reasons, we can put them in the same statement. So angle 1 is equal to 90, angle 2 is equal to 90. And then, whether you see this as substitution or as transitive, it's entirely up to you. But the measure of angle 1 is going to be equal to the measure of angle 2, and I see it as substitution. I'm substituting the measure of angle 1 in for 90. If that makes any sense. Or the measure of angle 2 in for 90, however you want to see it. Transitive, if you see it as we're sort of transferring the measure of angle 1 equal to the measure of angle 2 through 90. Okay? All right, now we know the measures are equal, then we know that the angles themselves are congruent. And that's because of the definition of congruence, or angle, congruent angles. It says if the measures are the same, then the angles themselves are congruent. Okay? So anyway, we developed that proof so that now we can use that theorem. If we ever decide that two angles are right angles, then our next step would be that angle 1 is congruent to angle 2, and the reason would be the right angles congruence theorem. We can use that as a reason now, the right angles congruence theorem. Okay? To show the two angles are congruent. All right? Next, if two angles form a linear pair of angles, we have to remember, we talked about this before. If two angles form a linear pair, two guys that form a straight line, a straight angle, therefore they add to 180, so that means we call them supplementary. Okay? And a linear pair is one of those things that we get to assume, and I'll show you that in a second. Quick question here, when are angles in a linear pair equal? Well, that happens if they're both 90 degrees or if they're both right angles. Then the linear pair, the two angles are congruent. Okay? All right. This next theorem says, it's called the congruent supplements theorem, and there's congruent complements theorem. But it basically says that if two angles are supplements to the same angle, then they have to be congruent. And there's why, right? So I want to walk you through it a little bit here. Just the proof, right? And it's not going to be a formal proof, but we can do this. If I know that angle 1 and angle 3 are both supplementary to angle 2, and let's say I measure angle 1, it's 30 degrees. And how big does angle 2 have to be? Since they're supplements, it's got to be 150 degrees. Well, that means that angle 2 down here is 150. Angle 2 is supplementary to angle 3. So what's angle 3 got to be? If you subtract it from 180, then angle 3 is 30 degrees. And so they're the same. 1 and 3 are the same. That means that if 1 and 3 are both supplementary to angle 2, then you can just jump down and say that 1 and 3 are congruent. And the reason you would use is the congruent supplements theorem. And you can write it like that if you want. Congruent symbol, abbreviate supplements, and theorem. Okay? Same thing for the congruent complements theorem. If two angles are complementary to the same angle, then they are congruent. Okay? And it's the same kind of proof, right? If angle 4 is 30 degrees and angle 5 is a complement to angle 4, subtract from 90 and angle 5 is 60. Well, if angle 5 is 60 and it's complementary to angle 6, then angle 6 is 30. And you can see that angle 4 and angle 6 are congruent. So, if I know that angle 4 and angle 6 are both complements to angle 5, then they have to be congruent. So I can just say 4 and 6 are congruent, and it's because of the congruent complements theorem. Okay? We'll put that to use in just a second. Now, back to things that we can assume in a diagram, right? Sketch and label vertical angles. Okay, vertical angles, you're looking for an X. You need two lines that form a straight lined X. Okay? And so there's two lines, and they form four angles. 1, 2, 3, 4, just like that. Well, we can assume straight lines in a computer-generated image. We talked about that already. So if that's the case, then I can assume that that's a straight-lined X. Now, the angles that are vertical are the ones that are back-to-back sharing a vertex. So in this picture, angle 1 and angle 3 are vertical angles. Angle 2 and angle 4 are vertical angles. And we can just assume that from a picture. There's not any formal definition or any sort of thing that we need to go through to say that. We can just say 1 and 3 are vertical, 2 and 4 are vertical, and that's by the definition of vertical angles. Now, same thing with a linear pair, right? A linear pair we can assume because they form a straight line. And we can assume straight lines. So angles like 5 and 6 here, we can say are a linear pair because we can assume that from the picture, from the definition of linear pair. Okay? Now, if that's the case, then it leads us to this next theorem, which is the vertical angles congruence theorem. Basically, the theorem says that vertical angles are always congruent. Okay? And here's the proof for it. We always start with a given. So we're given that angle 5 and angle 7 are vertical angles. We could assume that from that diagram. But angle 5 and angle 7 are vertical angles. That's given to us. Well, if that's the case, then if you look, don't worry about what I wrote down just yet. If you look, angle 5 and angle 6 form a linear pair. Okay? If they are a linear pair, then they're going to be supplementary. So I can say that angle 5 and angle 6 are supplementary by the definition of a linear pair. And the same thing with 6 and 7. They are supplementary because they're a linear pair. So by the definition of a linear pair, they're supplementary. So 5 and 7 are both supplements to the same angle. That means I can jump down and say that 5 and 7 are congruent because of that congruent supplements theorem. There's a use of that theorem we just took a look at a second ago. And if you look in here, 5 and 7 are those vertical angles. And so vertical angles are always going to be congruent. You're going to want to find vertical angles somewhere anytime in this class because they're going to be congruent automatically. Okay? And we can also use that from now on. Once we know that, we can just assume, from now on, we can get that diagram, we can just assume that angle 5 and angle 7 are congruent because of the vertical angles congruence theorem. Okay? So, now that we have this proof, basically what that means is, from this picture, I can just jump down and say that angle 5 is congruent to angle 7, and my reason would be the congruent, it would be the vertical angles congruence theorem. Okay? That's a reason we can use now. All right? And that's it. That wraps up this chapter. Your homework's out in Canvas. Make sure that you have that done next time.